So now we're going to look at a specific sort of structure, which will be known as a covered structure. So this notion has to do with the value of so-called closed terms in the structure. So firstly, we need to say what a closed term is. And this is very simple. It's a term in which no variables occur. So for example, in the language LA of arithmetic, the zero symbol, it's a constant. So no terms occur in it. So if I was to take 0 prime prime plus 0 prime prime times 0 prime prime prime, for example, that's a term, right? We build it from constants. There's 3 occurrences of the constant symbol 0, and we've applied function symbols to the correct number of arguments in every case. Notice also that I've used the infix notation over here, which we allow ourselves to use. So those are closed terms. Something which would not be a closed term, for example, is any variable, x, y, or any term that contains a variable. Suppose I want to say 0 prime prime plus x times 0 prime. So these will all be not closed because they contain variables. All right, so next we need the notion of the value of a term in a structure. Structure M for a language L. All right, so this captures what you would imagine. When I've got a structure and I've got a constant symbol, then the structure comes with an interpretation for that constant symbol. That is the value of this constant symbol. And then if I've got a closed term, then I can essentially compute the value of these closed terms inductively, starting with the value of the constant symbols. So if I've got a constant symbol, then we will say the value in M, so the superscript M, the value in M of this closed term is simply the interpretation of this term in the structure. It's what the structure tells us this constant symbol is interpreted as. And then if I've got, here comes the inductive step, if I've got a function symbol applied to closed terms, and so the whole thing is a closed term, then we simply compute this inductively. So the value in M of a closed term of this form, f, suppose f is an n-place relation symbol, so it takes arguments t1 to tn, where they are now all closed terms, then this is simply, well, take the function interpreting f in the structure, the actual function interpreting this function symbol, and apply it to the values in M of the arguments. And that is then the value of this term. So let's look at an example of the value of a closed term. Let's consider our language of arithmetic, and let's consider some of those closed terms we had up there. So, well, clearly the value of the constant 0 was just the natural number 0, because that is the interpretation, that is what the object of the domain that the interpretation assigns to this symbol over here. And I'm trying to make this look like a slightly flatter square, a little 0 than this 0 to make the distinction between the symbol in the language and the actual number in the domain. All right, so this would be the val in, so we call that structure n, right? So let's consider the value in our standard interpretation or standard model for the language of arithmetic of that term we had over here, 0 prime prime plus 0 prime prime times 0 prime prime prime. All right, so recursively, I need to go and, now we'll do this according to the inductive definition, but as you'll see, we could actually figure this out much more quickly than really going step by step through the inductive definition. So we've got the addition symbol being applied here. So what I need to do is I need to apply the interpretation in n of the addition to the value of in n of 0 prime prime, and as the other argument I need the value in n of 0 prime prime times 0 prime prime prime. All right, but let's look at this. So what I'm doing here is I'm going to do a couple of steps in one now. What I'm doing over here is I need to go now and look at the value of 0 prime to which I've applied the interpretation of the prime function symbol here. Now, what does the prime function symbol do? It just adds 1. Now, so if what we would get essentially here is I would get 0 plus 1 plus 1. All right, and here then this is just the plus in the natural numbers that I'm writing now, not the symbol. And here I would get 0 plus 1 plus 1 times 0 plus 1 plus 1 plus 1. Right? So what I've done is I've done this inductive unpacking of this value over here and this value here. I've done that in one step. But strictly speaking, I would need to apply clause 2 here to each of these primes in here and then fall back on clause 1 to determine the value of this little symbol over here as the integer 0. Similarly here, I've used the inductive clause 2 to turn this into the multiplication of natural numbers, and then I applied the inductive clause to unpack that again. So one can really write this out line for line for line, but this is what you will end up with. So what do I have here? I've got the natural number 2. Here in brackets, I've got the natural number 2 times the natural number 3. So what I'm getting here is 2 times 6, which is just the number 12. So that would be the value of this closed term in the standard structure or the standard model for the for arithmetic. So what then is a covered structure? A covered structure is a structure for a language in which every element of the domain is the value of some closed term, right? So give me any element of the domain, then I need to be able to write some closed term, and its value needs to equal that domain element. So now, see if you agree with me that the standard structure, or standard interpretation, or standard model for the language LA of arithmetic is a covered structure, right? Well, let's start at 0. 0 is the value of some covered term, right? It's the value of the constant symbol for 0. 1 is the value of 0 with a prime applied to it, and so forth. Give me any natural number, give me the natural number m, and 0 with m little primes applied to it, its value will be that natural number m. All right. If I took a non-standard interpretation of this language over here. For example, if I took the integers, right, would that be a covered structure? Would I be able to write every integer as the value of some closed term? Or if I took the rationals or the reals, would they, and extended the interpretation of LA in the obvious way to those, would they be covered structures? See if you can decide whether they will be.